Everything we observe around us is made from the same stuff. Whether that be me, you, or a galaxy 1,000 light years away, everything is composed of just 17 particles. Together, these elementary particles create something called the Standard Model, a theory which describes the particles and their interactions. The Standard Model is further divided into two groups, the fermions and the bosons. The primary distinction between the two groups is that the fermions follow the Pauli exclusion principle, whereas the bosons follow some rules devised by the Indian physicist Satyendranath Bose, thus the name bosons. These gauze bosons are force-carrying particles as they are the cause of interactions among fermions. These interactions are governed by the four fundamental forces: gravity, electromagnetism, the weak force, and the strong force. However, gravity is still quite an enigma, and its effect on subatomic particles is so minuscule and negligible that it is not included in the Standard Model itself. Let's start off with the weak force. In a nutshell, the weak force is why you see a huge yellow ball of plasma in the sky when you look in the day. The weak force mediates a process called nuclear fusion. In nuclear fusion, lighter particles fuse into heavier particles. This process starts with hydrogen and ends with iron. In the process, the sun emits approximately 10 to the power of 45 photons every second. Moreover, the weak force is also responsible for the decay of heavy particles into lighter elementary particles. The weak force also allows up quarks to switch into down quarks and vice versa. The operators of the weak force are W and Z bosons. However, these bosons are about 100 times heavier than protons, in turn making them unstable. They only appear for a short amount of time, which is why the weak force is, well, weak. Next up, we have the electromagnetic force, the second strongest of the fundamental forces. In a gist, electromagnetism describes the interactions among fermions that have a charge. This includes everything except neutrinos. Particles with the same charge repel, and particles with different charges attract. The force-carrying particle for the electron force is the photon. The exchange of photons is what mediates electromagnetism. If an electron absorbs a photon, it jumps to a higher energy state. Emitting a photon means going down to a lower energy state. Electromagnetism is what keeps electrons in orbit. So if there's someone you want to thank for keeping you in one piece, it's electromagnetism. Last but not least is the strong force. True to its name, the strong force is indeed quite strong. For comparison, it is about 100 times stronger than electromagnetism, 10,000 times stronger than the weak force, and 10 to the power of 39 times stronger than gravity. The only thing is, the strong force is only strong at subatomic distances. The role of the strong force is essential. It binds the three quarks in a particle together via something called the color charge. However, color charges need a video of their own, so we will not be discussing them in this video. Anyways, the gluon is the force-carrying particle for the strong force. It uses something called the flux tube to connect quarks together. Quarks are unable to exist on their own, which is why we only see quarks in groups. Seems friendly. There are actually 5 bosons, not 4, the fifth being the Higgs boson. However, that is a topic for another video. 2. The weak force only interacts with particles that have a negative integer spin. We call these particles left-handed. And number 3, gravity is not in the Standard Model. However, physicists have still theorized a particle called graviton, but no one has found it yet. Overall, these forces work together, each in their own different and unique ways, to form the world as we see it today.